Hello everyone, I am Alok Kumar and today I welcome you to the first lecture of the 3 lecture series that we will do on vectors. As such, this chapter sees routinely many questions both in JEE Mains and JEE Advanced, so it's well worth your time to complete this chapter and go through it. So let me now share my screen with you all and start the chapter. Okay, so first concept that is of fundamental importance in vectors, basically it's a foundation. So this kind of thing is called, we start with a very simple concept but still having lots of applications. So we call it linear combination. So we call it linear combination. So let me give you a definition that a vector R, let's say some vector is there, a vector R. Now vector R is said to be a linear combination, that is LC, linear combination in short of the vectors say A, B, C and all those vectors if there exist scalars x, y, g, etc. such that R equals xa plus yb plus gc. So it means if you can write R as this kind of thing, x times a plus y times b plus g times c. So it means they all are multiple of a, multiple of b, multiple of c, or just adding them. So the definition says that a vector R is said to be a linear combination of the vectors a, b, c and all if there exist scalars x, y and g, etc. such that R equals x times a plus y times b plus g times c. In fact, for example, I can say that 2a minus 4b plus c, or a plus 2b, or a minus 3b plus 11c, they all are linear combination or LC of vectors a, b and c. Three combinations are especially useful to us. X times a, that is called the scalar multiple of a, so x times a. Then x a plus yb means linear combination of vectors a and b. X, y are some numbers and others. And third is xa plus yb plus gc. So it means this is a linear combination of three vectors x, y and g. So when you are restricted to a plane, when you think of a plane a and b, then of course this is the one. So xa plus yb, it will expand all the plane, means every vector that is in the plane of a and b you can write in terms of x a plus yb, provided a, b are not collinear, some sort that we will see later. Similarly, if we have got a, b and c suitable vectors, like if you have got a, b and c suitable vectors, we will get to know that suitability means that they are non-coplanar. So if these vectors are there, a, b, c, and they are suitable vectors, then any vector r skew vectors, means not in this plane only. A, b, c also need not be planar. So any vector r in a space can be expressed as a linear combination of a, b and c for some scalars x, y and g. So this is your thing. It's really beautiful. Now, similarly, we now define a concept called collinear vectors. Collinear vectors, as name tells, collinear. So vectors a and b, these are called collinear. They are called collinear. Remember, in maths, definition is everything. It's sacrosanct. Means everything follows from definition. The more you have mastered it, the more you understood it, the better you are in applying them. So if a and b are collinear vectors, it means that A equal to lambda b, they are called collinear if A equal to lambda b for some scalar lambda. Means some scalar is there, lambda, A is 2b, A is 3b. They are also called, say, parallel vectors, because you know that vectors can be aligned, right? So A is lambda b for some, this one. Next, we will go to define coplanar vectors. Coplanar vectors. So now we are saying that ABC. So ABC are called, they are called coplanar. They are called coplanar vectors. Coplanar vectors if one of them, say A, without loss of generality. So ABC are called coplanar vectors if one of them, say A, without loss of generality, can be expressed. So if one of them, A, can be expressed as a linear combination, of the other two, that is, you are saying A equal to lambda b plus mu times c for some scalars. They are mostly real numbers. For some scalars, lambda and mu, then we will call that these three are coplanar vectors. Obviously, any two vectors, if you take, they're always coplanar. So it arises only when the third vector is also there. So three or more vectors. Now, once we have done with this, we have got two important results, two results that are really important. Two results. One is that given any two, this is the basis of what we normally do. Given any two non-collinear vectors A and B. So given any two non-collinear vectors A and B, every vector R can be expressed. Every vector R, that is, we can add, that is coplanar with A and B, can be expressed as a linear combination of A and B. That is, R is XA plus YB. That is any two non-collinear vectors. Of course, if one is zero, it cannot happen. So next will be given any three non-coplanar vectors A, B, C, every vector R, now it is a space, every vector R can be expressed as a linear combination of A, B, and C. That is R equals XA plus YB and GC. This also we can do. Moreover, these representations, as you might have guessed, these representations are unique. That's the beauty of it. They are unique. Means that given any two non-collinear vectors A and B, every vector R that is in plane with A and B, so A and B are here, and every vector that is in plane with A and B R can be expressed as a linear combination of vectors A and B. That is, there are scalars X and Y such that R equals XA plus YB. And obvious generalization will be in three dimensions, that given any three non-coplanar vectors, this time it is non-coplanar, given any three non-coplanar vectors A, B, and C, every vector R can be expressed as a linear combination of vectors A, B, and C. That is, R equals XA plus YB plus GC, where X, Y, and G are suitable scalars. And the most important point, that these representations are unique. That's what we do when we compare the things. Okay, so then other definition will be that linear dependence and independence. So one is called linear dependence, and of course then linear independence. Now, this is also one of the important thing. So a system of vectors, we define that, in fact, we define linear dependence first, LD, and we will negate LD to arrive at LI. So we say that a system of vectors, A, B, C, etc., is said to be LD, linearly dependent, if there exist scalars x, y, g, not all zero, means at least one is non-zero, not all zero, such that zero vector is x times a, y times b, g times c, and all those numbers. So I call it like this. So I repeat, a system of vectors a, b, and c is said to be LD, linearly dependent, if there exist scalars x, y, and g, not all zero, I stress not all zero, such that 0 is xa plus yb plus gc, and so on. Now this looks very dry. Let's try to give an intuitive meaning to it. This just is trying to say that if they are LD, if the vectors ABC are LD, means that you can get zero. You can get the zero vector, you can create the zero vector as a linear combination of these vectors. If it is not dependent, then you can't create. So not all zero means at least one must be non-zero. If the only way to get zero is by taking all x, y, and z is zero, then of course we will say that this means that the vectors ABC are linearly independent, means no linear combination of them except all scalars being 0, 0, 0 can give you vector 0. So we say this way again, that a system is not LD, a system which is not LD is said to be LI. Means if it is not linearly independent, it means it is linearly independent. They are just opposite of each other, this concept. If you are A, then you are not A. So not A equal B. So you are saying that if it is linearly dependent, it is not dependent, it means it is linearly independent. So it means that for these kind of things, linearly dependent, star will imply that x equal to 0, y equal to 0, g equal to 0, and all such numbers. Means if the vectors a, b, c are linearly independent set of vectors, then this relation star will always give you x is 0, y 0, g 0, means every scalar will turn to 0 if they're linearly independent. So this is the definition of linearly dependent and independent. Then we have got two important results based on that. So two results. One is called that a pair of non-zero, non-collinear. Remember we defined collinear, non-collinear before. So a pair of non-zero and non-collinear vectors is Li, linearly independent. And similarly, a triple of non-zero we retain, non-zero, but we are in plane now, we are now space, so there is no question of non-collinear, so we'll say non-coplanar. So we are saying that a triad of non-zero, non-collinear vectors is again linearly independent. And you can have a corollary that every set of 4, of course then OR mode, so that is in bracket. So every set of 4 vectors, I need not write, every set of 4 vectors is linearly dependent. Whenever you write something in bracket, it's like clarifying. It's like clarifying what has gone before, clarifying what is being said. So we are saying every set of 4 or more, means if true for 4, then of course for every set of 5 we'll get 4 also. So every set of 4 or more vectors is linearly dependent, because your space is in 3 dimension. It is everything is set with respect to 3 dimension. Similarly, we have got another concept, that is basis, components and coordinates of a vector. So this tells you that let ABC be 3 non-coplanar. So let ABC be 3 non-coplanar vectors. So we know that I can write R, any vector R, I can write as XA plus YB plus GC. Means if ABC are 3 non-coplanar vectors, then I can write everything, and non-zero of course, so I can write R equal to XA plus YB plus GC. Or I can say that 3 vectors, and we say that okay, they are Li, linearly independent. So it means now we will say that vectors ABC, this set of 3 vectors, this set is a basis set. This set is a basis set. Means that you can write any vector R in terms of these A, B, and C, because they are a linear combination. This is linear and this is linear independent. This is linear independent. So the set of vectors ABC with respect to which we are writing coordinates of R is called a basis set. The numbers XA, YB, and GC, they are called the components. They are called all vector components. They are called components of vector R with respect to or relative to, components of R relative to the basis set A, B, and C. So they are the components. And X, Y, and G, they are called the coordinates of vector R, of course relative to the basis set A, B, and C. Means given any basis, we can write R as a sum of these 3 vectors, these 3 numbers. So this will be called the components. So this is XA, YB, and GC are the components of vector R, or they have been decomposed. So vector R relative to the basis set A, B, and C, and numbers X, Y, and G, they are sort of called coordinates of vector. For example, if you write usual thing 3i plus 4j plus 5k, this is some vector R. It means that corresponding to the set corresponding to the basis set ij and k, you know ij k form the basis of this one in a space. We always use it everywhere. So ij k is there. Now these 3i, 4j, and 5k, they are the vector components. So they are the components of R. And 3, 4, 5, they can be called the coordinates of R with respect to I, J, and K. So these are the coordinates. So they are sort of components, and they are sort of coordinates. So they are like vector components. And I, J, K is a basis set. So which is of course linearly independent. And then we do all the things. So I take up my first question, which uses these ideas. Students normally find this heavy or difficult because it's very abstract. The definitions are all abstract, where you really have to think of definition. It is not much calculation, it's just more, it is conceptual, less computational. Still computations are there. So problem says like this, that if a triad ABC is a base, so you are given that ABC is a base, triad ABC is a base, then you have to prove that A plus B plus C. So this is the first part. Then prove that A plus B is also a triad. And second, And second, you are saying that find the if x, y, g are coordinates of vector r, some vector r, relative to ABC, then find these coordinates, then find the coordinates of vector r relative to a plus b, a plus b plus c. So it tells you two things. It tells you two things. First, it asks you that, okay, in the triad of vectors ABC is a base, means the moment I say base, it means ABC are linearly independent. So it means any vector r I can write in terms of this. So they are saying that don't write in terms of this, write in terms of, in fact, a plus b, a plus b plus c. So first you must prove that whether this constitute a valid triad or not. So first answer would be like this, that you want to prove a plus b is a triad. So let us do like this. So I want to prove it is linearly independent or not. So I can write that suppose you are checking where li or not. So it is a question mark. You are saying suppose lmn are scalars. So you're saying suppose lmn are scalars such that L times A plus M times A plus B. ABC are already Li, so this we know. We are testing for A plus B, and A plus B plus C. That whether these set of three vectors, they constitute a linearly independent set or they don't constitute. They constitute a Li or if they don't. So I'll write here that we are asking ourselves that let Lmn be a scalar such that La plus Mb, La plus M plus B plus N times A plus B plus C is 0. Means we are assuming that a linear combination, watch out for my words, a linear combination of these three vectors producing a vector 0. If I can produce it such that at least one of L, M, and N is non-zero, then we are done. If we can't produce, means if this implies that L is M is N is 0, a scalar 0, then I will say that then conclusion will be that they are Li. These three are Li. These vectors A, B, A plus B plus C are Li. So we'll try to solve for other L, M, and N using the fact that ABC are Li. So what we are proving is that if ABC are Li, then so are. So we are proving if ABC are Li, then so are A plus B, and A plus B plus C. Now let us write it collecting the coefficients of A, B, and C. So this is A will get L plus M plus N times A plus M plus N times B and plus N times C equal to 0. Now, because A, B, and C, they are given, A, B, C are given to be Li set, linear independent set, it means that their coefficient must vanish. Means these all will become 0, 0, and 0 by definition of linear independence. Because we said that if you have got P times A plus Q times B plus R times C is 0, and A, B, C are linearly independent, then it must be the case that P, Q, and R all must be simultaneously 0. Means everything must be 0, 0, and 0. So using this, we get L plus M plus N equals 0, M plus N equals 0, and also N equals 0. It's an easy system to solve, and we can solve it bottoms up. So N is 0 means N 0. This means N0 means M0, and then here it gives you L equal to 0. So it turns out that L, M, and L all are 0. And if all are 0, then we know that yes, that this is linearly independent. And see, we started with element here. So it means it gave you that in fact the the set of vectors a plus b, and a plus b plus c, they all are linearly independent. So we have proved this one. Just to remind you, it was given that triad ABC is a base, means they are Li. Prove that a plus b, a plus b plus c is also a triad. So it is correct, because we proved that if ABC are linearly independent, then so are a plus b, a plus b plus c, by using a straight definition. So I started ABC are Li, and then I said that okay, so we have to prove this. So because so we are testing that whether these are Li or not, Li or not. So test is that select numbers or assume numbers lmn, and solve this for lmn. We found that all are zero. That tells us that yes, indeed they are all linearly independent. So this constitutes a triad of vectors. It is a basis vector. It can serve as a basis vector. You know that. So it tells you something like this, that if I, j, k are basis vectors, somebody can also write that I and then a plus b. So I can choose I plus j and I plus j plus k. They will also form the basis. Means some number 11i plus 4j plus 5k with respect to ijk has got this as coordinates 11, 4 and 5. 11, 4 and 5, they have got this as coordinates 11, 4 and 5. Similarly, this can also be, there be some numbers such that I can write this as I and then I plus j and then I plus j plus k. Means I can choose these numbers such that I'm able to express this in terms of these three, because they are linearly independent. And so every vector R can be expressed as a linear combination of these three vectors. So this part is done. The other second part was that suppose express the coordinates of R related to A, B, and C, then find coordinates of R relative to a plus b, a plus c, of course in terms of x, y, and g. So it means what is given is this, that already given that R is x times a plus y times b plus g times t. This is the meaning of saying that x, y, and g, they are the coordinates. They are the coordinates of R relative to set of vectors a, b, and c, or relative to basis, or relative to basis a, b, and c. Now we ask ourselves the question that how can we write R equal to some number times a, then some number times a plus b, and again some numbers times a plus b plus c. So we want to find these scalars, that how we can write. So let's say that these scalars are L, M, and N, or let me change the symbol and use lmn is all right. We can go ahead with it because where x, y, and g are given. So we are writing this like this. It means that this R is, again we can combine the terms. So we will get L plus M plus N times A. Then again we will get in B M plus N times B and N times C. It means same R can be expressed as this. So is this. It means already we know that R has got representation x, a plus yb plus gc. So R can be written as a linear combination of ABC, and coefficients are x, y, and g. And here coefficients are this. So they must be same. Why? Because of representation being unique, because of uniqueness of representation. So because of this uniqueness, we are sure that yes, these two are indeed same. This R and this are same. So this must be same. And so coefficients of A must agree with this. Coefficients of B must agree. And coefficients of C also must agree in both representations. And so I'll get L plus M plus N equal to X. I will get M plus N equal to Y. And I will get N equal to Z. Again, I can solve from here. So I want to get now LMN in terms of X, Y, and G. So N equals G, M equals y minus n, that is y minus g, and L equals x minus m minus n. So x minus m plus n. So x minus m plus n is given to be y. So x minus y. So we say that in terms of this one, R is written like x minus y times a plus y minus z times a plus b and plus z times a plus b plus c. Means with respect to a plus b and a plus b plus c, the coordinates of R are x minus y minus g, and g. Earlier it was x, y, and g with respect to. So we started like this. So this is xa plus yb plus gc. So with respect to a, b, c, the coordinates were x, y, and g, a, b, and c. Now you change the vectors, basis vectors, of course, coordinates will change. So these are the new coordinates. So for example, if you are given these numbers were 2, 11, and 18, so here your answer will be different. It will be something like minus 9, and then you will have y minus g, so it will be minus 7, and then g, that is 18. So this kind of thing can be asked. This is one. Now let me use one geometrical application of coplanarity, or those concepts, geometrical application. So we start with a problem. I will give a solution using vector, a different solution which is much shorter. But of course, the chapter is vector, so we must get our mastery over vector first. So this is a triangle ABC is a triangle, and what is given is this one. So triangle ABC given, I write here and make a figure. Triangle ABC is here, and then you are given that BD over DC is 3 over 2, CE over EA is 1 over 3. So this is D is a point. So this is 3 is to 2. Now, so let me erase and write it little beautifully. So this is 3 times 2. So 3 is to 2, BD is to DC, and C is to EA. There is a point E here. So C is to EA is 1 is to 3. So this circle I am showing just for ratios. They are not length, they are ratios. That thing indicates that. So this BE and AD, let it meet at P. So BE and AD, B and AD intersection, that is just the point P, and CP meets AF at B, and CP meets AF AB at F. And then your job is to find AF over FB I want to find. So they are the two, they are called sometimes Chevians. This is called Chevian, Cevian. So you can call it Chevian or Cevian, but Chevian is the preferred spelling, so or pronunciation. So this is Chevian. So you have got two Chevians, AD and B, just like median is something that is 1:1. Chevian can be any ratio. It just emanates, it just issues from a point and goes and meet the other side, opposite side. So there are two Chevians, AD and B. These Chevians meet at P, okay, and ratios are given. And the third Chevian from C, so C and P are joined, and then CP extended meets AB at F. Our goal, our job is to find AF over FB. We can do it very easily using geometry, one theorem called Cheva's theorem, which I will tell you just after the solution. But right now, let me get my hands dirty by using some vectors. And vectors also will tell you a nice method of doing, albeit little longer. But you will learn so many things in the process. So first of all, we should just have some suitable system. So I will write this C. This C I will take as origin. I can take origin. That is your experience in 2D geometry also, that you can choose your origin as you wish to simplify your calculations. So this is my origin, and this I will write as A, and this as B. They are my position vectors. So my position vectors are A for A and B for this point B. That's all right. And now once that is done, I can use the good old section formula to get E and D quickly. So this ratio was 2:3. Remember, ratio was 2:3. So you will get this number as 2 by 5 times B. So position vector of this is 2:3. This was 1:3. So 1:3. So you will get this as 1/4. So this E you will get 1/4 of A. So we get D, we get E, that is 1/4 of A, that is position vector of E, and position vector of D, we get 2/5 of B. So far, so good. Once we get this, now my job is simple. Now let me write equation of AD and B the way you write in 2D geometry. So equation of line AD, vector AD, this AD, and I will also write vector equation of line B. Very simple. So now AD, I will write AD as any point AD can be taken as R. So I can write that R equals A plus lambda times 2/5 of B minus A. If you are wondering, let me do the background work. That I'm saying just this, that if there is a point A here and there is some point, or say P here, and there is some point Q here, you want to find the equation of line PQ. Then suppose any point PQ is R. This is the coordinates of any point, arbitrary point R. So I can say that vector R minus P is collinear with vector Q. Vector R minus P, or vector rather Q minus P. So I can say that vector R minus P is collinear, or say parallel to Q minus P. And so R minus P is lambda times Q minus P, where lambda is a scalar. And so I can write R equal to this little thing, P plus lambda times Q minus P. Take numbers. Say suppose here you have got 2i plus 3j. Here you have got 5i minus 11j. And you want to find the equation of line AB. Then you can just say that this R is nothing but 2i plus 3j plus t times, or some scalar times, difference of these two, means 5i plus 11j minus 2i minus 3j. That gives you 2i cap plus 3j cap plus t times 3i cap and plus 8j cap, and we are done. It means we are just saying that if you want equation of AD, so this is A and plus lambda. So this is position vector of A plus lambda times position vector of difference of vector D and vector A, position vector. So D and A. Similarly, BE, I can write R equal to B plus, start at B plus mu times some other coefficient, mu times 1/4 of A minus B. So these are the equations of AD and B, and they meet at P. So just as in coordinate geometry you solve, in 2D geometry you solve equation of line to find point of intersection, I can find P by equating. So for P, these values must be same. It's like solving these two. So I can get lambda and mu here, that it will be such that this minus A is B plus mu times 1/4A minus B. They must be both equal. And so I can collect the coefficient 1 minus lambda times A plus 2/5 lambda times B, and equal to A will be 1/4 of mu, so mu over 4 times A, and plus 1 minus mu times B. Now again, these two are equal vectors, and A and B are non-collinear because you can see that these OA and OB, they are non-collinear, and so they're not parallel, means, or anti-parallel. So it is like this. It means the coefficients of A and B vector must agree. That gives you 1 minus lambda is mu over 4, and 2/5 lambda is 1 minus mu. I can quickly solve it. So I can write from this second equation, 2/5 of lambda is 1 minus mu. So mu I can write from here, mu is 4 times 1 minus lambda. So this is 1 minus 4 times 1 minus lambda. That gives you negative of 3 plus 4 lambda. That gives 4 lambda minus 2 lambda over 5 is 3. And then you are getting 18 lambda over 5. is 3, and so lambda you are getting as 5 over 6. So lambda is 5 over 6, and if that is so, then mu also you can get easily. So your mu becomes mu by 4 is 1 minus lambda 5 over 6, so 1 over 6. So mu becomes 4 times 1 over 6, so 2/3, 2 over 3. And so we get lambda 5 over 6, we get mu 2 over 3. Such is the power of vector algebra. And so we get 5 basis 2 over 3. And let's see how this rewrites. So P, coordinates of P, which I call RP, coordinates of P are P. That was, you can check anyone, either this or this. Let me check this one, 1 by lambda A. So this is 1 minus lambda A, and plus it was 1 minus lambda A, and plus 2/5 of lambda times B. So 2/5 of lambda times B. So 1 minus lambda, my lambda was 5 by 6. So this is 1 minus 5 over 6 A plus 2 by 5, 5 over 6 B. And this we can write as A over 6, and plus this is 5 cancels. So 1/3 of B. And this again I can rewrite, and this I can simply write as this is 1/3 of this is A plus twice B. So that tells you that you are getting 1/3 of A plus 2B. So let's write the coordinates of this diagram. I will reproduce A and B. So this whole diagram is not needed. Now here it is A, here it is B. Your A was A, B was B, and the point F which you wanted, that F point is 1/3 of A. So I'll write 1/3 of A and plus 2/3 of B. This is the point. You want AF is to FB. Section formula tells you that AF over FB is 2 over 1. Why 2 over 1? Because it's like you are writing this as, this is like if you take A and B, and if you take 2 and 1 here, so you will get here coordinate of F as, so F you will get as twice A. So you will multiply this way, this and this, cross multiply. So you will get twice A plus 1 times B, and over 2 plus 1. So that is twice of A plus B. And then it was, of course, it's not 1:2, it's 2:1 that I discussed early. So let me correct it, 2:1. And so I can write here as this one. So I can write here this A into 1 in this one. So you will write like A plus 2B. So A plus 2B upon this, that gives you 1/3 of A plus 2B. That's what we got here, 1/3 of A plus 2B. And so we say, so we are reading it in reverse order as it happens, because coefficients of A is 1, 2 is there, 1 is, so not dot 1, I write simple, and this is 1 plus 2, 3. It means from A ends it is 2, and this one, so this 2:1. So this answer is 2:1. Now solution using Cheva's theorem. Second solution, which is pretty elegant and much quicker, much faster. So that comes through something called Cheva's theorem. It is called Cheva. So Cheva's theorem tells like this. So let me give you the theorem first, that if you have got ABC as a triangle and point DEF are points here such that AD, BE, CF are concurrent, means 3 lines are concurrent at any point, say P, I don't care the point name because not required. So it means the Chevians AD, the Chevians AD, BE and CF are such that they are such that AD, BE, CF they are concurrent, they conquer at some point P. Then BD over DC. So then start at B. BD over DC times CE over EA times AF over FB equals 1. Of course, converse also is true. Any geometry book will tell you that converse also is true. This is not in JE syllabus because geometry is not that much there in this. This is like Euclidean geometry, but still, this result is very, very important. All of you must try to make use of this result. It will be just very handy at times. So let me repeat first that the Chevians AD, B, and CF are such that their AD, B, and CF are concurrent at P, and so there is some metric relation. Metric relation means involving lengths. So that is BD over DC times C over EA and times F over B equal to 1. So if this number is 1, they are concurrent. And if they are concurrent, this then product of these two numbers equals 1. So converse also is true. And the moment you write this, now I can go back to my earlier problem, which will finish in maybe a minute. So that is your C, A, and B was like this. There was a point D, AD. So this was AD, this was BE, and this was 3:2. So this was 2:3 ratio. So I'm writing circle in ratio. They're not length, 1:3, and the three Chevians mate. This is at F. We want F or FB. Let's just start Cheva's theorem. So use Cheva's theorem. Start at say vertex A and go to B and C and A in that order. So AF over FB times BD over DC times C. This point was E. C over EA equals 1. Now F over FB we want, so let's keep it as it is. F over FB. BD over DC we already know. That's plug in 3 over 2. And C over EA also we know that's 1 over 3 is equal to 1. So this AF over FB and times 1 over 2 equal to 1. That gives you quite quickly, rather much quickly, that this is 2:1. And so we are done. That this ratio we wanted, this ratio that we have determined to be 2:1, in of course agreement with the previous method, vector, which was a little longer. But then you should master both methods. In exam, of course, exam you will do by this method, no doubt about that. But because some new problems will require you to line equation of line and other things, so that tells you many concept thing. So I would say that example is more instructive. It is more instructive in the sense that it tells you so many things to deal about, that how to write equation of line, how to make linear combination, and all such things. So I highly recommend that you master both methods. And of course, you are smart enough to know in exam, of course, solution 2 is to be used, no doubt about it. Okay, let's go to some other things quickly. And one problem that has always haunted students in terms of calculation, maybe computations. So maybe I will make it a little easier. So if the vectors, it's a previous JE problem, if the vectors xi plus yg and not yg, so this is, let me raise, this is if the vectors xi cap plus j cap plus k cap, vector 1, I plus yj cap plus k cap, and I plus j cap plus z k cap. If these three vectors are, if they are coplanar, then we want to find, so then find the value of, or evaluate, then find the value of 1 over 1 minus x, 1 over 1 minus y, 1 over 1 minus g, this you want. And of course, for this to make sense, in exam it was given that x, y, g are not 1. Means none of these numbers equals 1, in which case they would stop defining and it would not make sense. So I'll do two methods. So first solution, which is from this, I covered the theory. So we can say this way, that because they are coplanar, so I can write xi plus g. So I can write xi plus g plus k cap, one of the vectors. So if three vectors are coplanar, it means one of the vectors is a linear combination of the other two. So xi plus j plus k is lambda times, I can write I plus yj cap plus k cap plus mu times I cap plus j cap plus g k cap. And then I can of course equate the coefficients. So I can write here lambda plus mu I cap, and then I can write lambda y plus mu j cap, and then lambda n plus mu times g k cap, and we can equate coefficients of I cap, j cap, and k cap because they're same vectors. There must be unique representation, and so these numbers all must be equal to this, this, and this. We can get a system of equations, and we can do our job. That will be lengthy, but you do try it later. The second solution, which is amazing, is this way. So this will be that what we are doing is that we are using something from the triple product. We are saying that if ABC are, although we'll cover it in detail in other lectures, preferably third lecture, if ABC are coplanar, then box of ABC is 0. And we know box product that if A equal to, I will take it for granted, if A is A1 I cap plus A2 j cap plus A3 k cap, B is B1 I cap, B2 j cap plus B3 k cap, and C is C1 I cap plus C2 j cap plus C3 k cap, then ABC is easily written in terms of determinants, and that is A1, A2, A3, B1, B2, B3, and C1, C2, C3. Very useful form of representation of ABC, box ABC. It's this determinant. So this is 0. So I can write here. Now I know the coefficients that these vectors are x I cap, y j cap, j cap plus k cap. So it means in determinant language x11 and then 1y1 and 1g equals 0. And I want to find some value. So let me first write that. Let's leave the row unchanged. Number 1, R1, and R2, I will transform R2 minus R1, and R3 also transform as R3 minus R1. So x11 is unchanged. This is unharmed, unchanged. So this is unharmed, unchanged. And you write this is 1 minus x. This is y minus 1. This is 0. And again, R3 changed to R3 minus R1. Subtract corresponding elements of R1 from R3 to get 1 minus x, 0, and z minus 1 equals 0. Now again, one more thing. Don't expand naturally. Expand using something called Sarus rule of expansion, that tells that if you have got A1, B1, C1, A2, B2, C2, A3, B3, C3, you expand as, first you take along principal diagonals. So you form A1, B2, C3. So you form A1, B2, C3 plus, then you form C1, A2, B3. So this is 1 and this one. So what you are doing, that you are on this kind of thing. You are doing this one, that you have got these numbers here. So first you are using this one, then you're using this and this one, and then last you will use these two and this one. So let me write A1, B2, C3 plus C1, A2, C1. This is C1, A2, C3, and then A1, A1, B1, C1, A2, B2, C3, A3, B3, C3. So I'll get A1, B2, C3, and I will get, this was C1, A2, B3. I will get C1, A2, B3, and then plus you will get B1, C2, A3, and negative I will do. Same thing I will repeat along the other diagonal. So that is A1, B1, C1, A2, B2, C2, A3, B3, C3. I will go like this. So that is A3, B2, C1 minus A2 plus A2, B1, C3 and plus A1, B3, C2. So we will get like this. Here, I will first use this one. First, I use this one diagonal. This is this x times y minus 1. So it is x times y minus 1, g minus 1. First this one. Then I will use here. So 1 and 1, 1 minus x and 0, which will give you 0. So this is plus 0. Then I will use this kind of thing, that this 0, and then I will give this 1 minus x, and then this one. So again, it is 0 anyway. So it is 0 and negative. Then I will use along other diagonal. So this is this one. So that is negative of 1 minus x, y minus 1. And then I will get one more, and that is negative of 1 minus x times g minus 1 equal to 0. Now, because I want my answer in terms of x, y, and g, so what I can write 1 minus x equal to p, 1 minus y is q, and 1 minus g is r to simplify my calculation. So if that is the case, here I can write this x goes as 1 minus p, and times this I can write as 1 minus e y and 1 minus g because sign will change. So this is q times r, and negative this I can write as plus. I can write plus, this is 1 minus x, 1 minus y. Here also it is plus 1 minus x, 1 minus g equal to 0. So that gives you 1 minus p times qr plus 1 minus x is p, so p times q, and plus 1 minus x p times 1 minus g, that is again r, equal to 0. So that gives you that I can write this as qr minus pqr plus pq plus pr equal to 0. Take pqr to the right side, and so I can write pq plus qr plus pr is pqr. I can divide by pqr on both sides because none of them is 0. So that gives you pq plus qr plus rp upon pqr is 1. And that in some order, 1 by r plus 1 by p plus 1 by q equal to 1, which of course I can write 1 by p plus 1 by q plus 1 by r equal to 1. And we get back to our p, q, and r. So 1 by 1 minus x, 1 over 1 minus y plus 1 over 1 minus g, that equals 1. So you wanted this value equals 1. So that's a simple method. So here you are also able to use the determinant expansion. That is crucial. So my advice is don't expand directly, use Sarah's rule. So Sarah's rule already is like written, but then I can just highlight one point that or write in other ink that if you have got a1 b1 c1 a2 b2 c2 and a3 b3 c3, if this kind of thing is there, then I will use a different pen. So I'll use this kind of thing. So first is that first you are using these things a1 b2 c3, then other color, this you are using, use c1 a2 b3, and the third one, the last one that you use, say different color, you choose b1 c2 and a3 all plus. So you will get a1 b2 c3 plus b1 c2 a3 plus c1 a2 b3, and then along principal diagonal now you change the color and go along a1 b1 c1 a2 b2 c2 a3 b3 c3, and this time let's do this way, that you will get a3 b2 c1, this is 1. Then you can get this one, you can get a1 c2 and b3, and other you can again get this kind of thing, that b1 a2 and c3. So let me write this again. So you are getting something like this is negative of a1 b2 c3. So this is rather a3 b1 c2, so this is erased. So you will get negative of a3 b2 c1, this is this one, and plus a2 b1 c3, and plus this is a1 b3 c2. And so you are getting this positive, this 3 terms positive, these 3 terms negative. And if you write these two, this is what is called your Sarah's rule. So those who have not mastered it, I request them to read up it on and try to find occasion to use it. Then only you can be more proficient. Okay, so uh, that's now it's time for me to go. Let me stop sharing. Okay, so that's all for today. Let's